Audio Jungle. Audio Jungle.
All right. So in today class, we have to discuss torsion, which is very important gate point of view and any one day exam. Okay. So torsion. Okay. So here we have to discuss the analysis for the shaft. Okay. And that shaft is what basically connected one shaft to another shaft. We have two different methods, series and parallel. So based on that also we have to get the formula and we have a numerical. Okay. One more formula just for if you see the bending stress in beam, that time also you had seen one formula, bending formula called. So here we have a torsion formula, that is a master formula, that also we have to see. We have to check what will be the uh, angular deformation. Okay, like in case of bending you had seen the deflection which was in y direction. So here because of the twisting moment we have a deformation, but it will be a angular deformation. Okay. That we have to discuss. So if you check in torsion, so earlier what you had seen, it was like bending moment. So in bending moment what you will see, okay. So in case of the bending moment you had seen there was beam, that was the bending of beam. So this was the beam, see, simply this was the beam. Maybe there was a that load was acting, which was the bending load, or you can say it is the shear load, or maybe chances was there was bending moment, anything, maybe the load or maybe the moment. Okay, so because of this direct load you will get bending stress, no, or maybe bending moment you may have. So what was happened that time, you had seen there was the deflection, and that time if the load is what acting in this way or moment is what acting in this way, then this beam will be deflected in this way. If it is elastic beam, so it will be deflected in this way. Okay, so this was the condition. Okay, so this deformation what you had seen in case of the bending moment, here the bending moment it was along axis. Okay, bending moment it was along axis, so it was along axis. But now we are going to discuss torsion. So in torsion what will happen, suppose this is what shaft. Okay, this is what shaft. So basically shaft is what, it's a member, usually a circular cross section member you can say. And this shaft you may have seen in many mechanical uh, uh, cases, like maybe for the gearing, for the wheel, for the rotor. In fact you had seen shaft between compressor and turbine, so many places you have seen. So this shaft is what basically a structural member, and it is the circular cross section. And basically what is the work of the shaft work is what basically to transmit power from one place to another place, you can say. If it is turbine, so from turbine to compressor, how you will transfer the power or how you will transfer the work, so with the help of shaft. Okay, so basically it will be the circular cross section you can say, and this member will basically will be used to support wheels, pulleys. Okay, it will carry torque. That's the work of this shaft and all. Okay, now so now just make this is a circular cross section shaft. Okay, so this is what now shaft here. Fine. Now for this shaft, how that twisting moment will be acting. So suppose this is what the axis, this is what the axis. So that twisting moment, it will be acting like this. So you may get the difference between bending moment and twisting moment. So twisting moment will be along, for bending moment it was along axis. So for torsion it will be the about axis, because this is the axis. So here this is nothing but torque. Here you have a bending moment, this was bending moment. So here we will have a twisting moment. It is called twisting moment. And in torsion, this twisting moment will be acting about axis. About axis. Check, it is about axis. So it's your choice what sign convention you want to take. It is clockwise or anti-clockwise. Generally we used to take about axis rotation. Clockwise will be the positive and anti-clockwise will be negative. So here you got this torsion is also nothing but called as twisting moment. So twisting moment, in fact, if you talk about the twisting moment, if you talk about the torsion, so it is basically for the shaft. Okay, it is the circular cross section and it is a rotatory device. One end may be connected with the turbine and another end may be connected with the compressor or pulleys or anything. Hope you understood this. Now this torsion, I must say, this torsion, this name may be different book, you may get different names, so don't confuse this. Twisting torsion may also called twisting moment. It may also call torque. It may also called as axial couple. Okay, it may also called as axial couple. So these are the different names. So if you say torsion or torque or twisting moment, so it is basically for the structural member which is the circular cross section. Okay, and shaft is basically the circular cross section member. So this is what shaft. So all the analysis you will do here for the shaft. All right, hope this one is clear to everybody. Now if you say torsion of circular shaft, so just like for the bending of beam you had seen earlier, and it is torsion of circular shaft. So you had seen that both this is the beam and bending moment is what applied like this, and this is what circular shaft here. Okay, so in both cases we have a derived standard formula. So as I told you in starting only, here for the few derivation I must say not required, so no need to go for the derivation. This is what bending moment. And here about the axis we have a torsion, so this is what T or twisting moment, this is the bending moment. So in both cases you had seen the standard formula. Here you had seen bending stress formula, and here you have a torsion formula or equation of shaft subjected to torsion, or simply I will write torsion formula. Okay, so in this formulation you had seen it was sigma upon y is equal to it was m divided by I, and it was E by R. So in the same way we have here the formula tau divided by R, okay, is equal to T divided by J is equal to G theta divided by L. It's just like an analogy. Okay, why I'm saying analogy? Because here it was bending moment, so bending stress, sigma was bending stress, m was bending moment. Sigma was bending stress and m was bending moment. Here tau is the shear stress, so T is what? Twisting moment. Twisting moment or torque. Okay, and it will be along axis. This will be along axis. Bending moment will be acting along axis, and here it will be around axis. Around axis. Okay, this should be very clear to everybody. Now, so earlier, just like for the bending bending of beam, and in that there was the Euler-Bernoulli beam and there was the assumption. Similarly, we have here also the assumption. So now if you talk about the torsion equation, so tau by R is equal to T by J is equal to G theta by L. Okay, here all the components I will write. Here this derivation is not required, as I have mentioned many times, but if you check the standard formulation, so this tau by R is equal to T by J is equal to G theta by R, from where you will get. So this is the concept basically. If you check, if you take one shaft here, like here this is the shaft I'm taking, this is the shaft, okay. Now for this shaft, definitely if this side it is connected with the fixed end, this side it is connected with the fixed end, and if you apply along the axis, suppose here this is the, sorry, not along, around the axis, this is the axis, and around this axis if you are applying the torque, if you are applying the torque, which is called also twisting moment. Okay, so what will happen? check the diagram. So if I take 2 points, so earlier suppose this is the point, and once you apply torque T here, okay, so this point will be shifted at this point. So this is A and this is what B. But this end is what fixed. Okay, why it is happening? Because of the twisting, because you are applying the twisting moment. Okay, so you may have a deformation, and this deformation will be the angular deformation, which is also called angle of twist. Okay, so from here, from this center, how you will get that? So it will be like this only. See, you will get this deformation like this. About this is the center point here. So this angular deformation you may get. How you will get here? So I can say 2 points are fixed. So A and B. So from here, because this end is what fixed, so obviously it will make like this. So actually, if I show you with different colors, so I think it will be more clear to you. I just say okay. So here, after deformation, you may have this angular deformation, and this is nothing but angle of twist, or must say theta. This is theta, you can say. Okay, so okay, why this deformation you are getting from A to B? It is because of the torsion or twisting moment. Just say the length of shaft is nothing but L. Okay, obviously here the shear loading will be acting. Shear loading will be acting. Because if you apply torque in this way, so this is the fixed. So for the fixed torque, resisting torque will be like this. So this torque T will be the resisting torque. This will be the resisting torque. Resisting torque. Okay, and this is what applied torque here. So magnitude wise it will be same, but it is just opposite. Okay, so at the same time, if you take any section in between, so in between any section if you take, so that circular cross section inside I will get. So this will be the circular cross section. You cut that portion in between any point you can cut here. Okay, along the axis I can say this is the portion I'm taking here only. So this portion will experience the complementary shear stress. Because of this torque, shear stress it will experience, and this shear stress is nothing but tau. Okay, which is called complementary shear stress. It is called both. It is called complementary shear stress. Remember, this is the circular cross section, okay? Because you have taken this portion from the shaft, so this is the circular cross section. All right. Now for this, suppose this is the axis here. So from the axis, this distance is nothing but a small r. If you go for the complete circle, like here, so this will be the capital R. So from the center, this distance is what is small r. So now if you go for the formula, now we'll see the formula, tau by r, small r, is equal to T by J is equal to G theta by L. Okay, this is the formula what we have. So this formula comes from the derivation. As I mentioned, derivation not required at all. So all the things need to write. I mean, tau is shear stress, similarly T is the twisting moment or torque. Small r is the radial distance. At the surface of the shaft, small r will be capital R. Okay, so all those things need to write here. So it's shear stress, I must say induced. And why it is induced? It is because of induced due to twisting moment. Twisting moment means torque. Because of this torque, this shear stress will be induced. Okay, what is the theta? So theta is the angular deflection or sometimes called deformation, okay, of shaft. All right, now third point, this is the next, which is nothing but L. Here you have, so L is the length of shaft, radial distance from center. R is the radius of shaft, because shaft is the circular member, so radius you will have. Okay. Now what is the next? We have a G theta. So G is the, you might have heard in previous somewhere, it is the just like a Young modulus in bending. So in twisting or in torsion, it is called a shear modulus or modulus of rigidity. Okay, so it is called shear modulus G. It is called shear modulus, or it is called modulus of rigidity. It's called modulus of rigidity. And last is the J. Okay, so J is nothing but called as a polar moment of inertia. Okay, it is called polar moment of inertia, and I had already in my first lecture only I had explained what is the polar moment of inertia. So polar moment of inertia, what is the value of it? It's nothing but Iz. It's also called IP sometimes, polar moment of inertia, and it will be denoted by Z, or you can say moment of inertia about Z axis. That will be the polar moment of inertia, and it will be the sum of moment of inertia about x axis plus moment of inertia about y axis. If you are taking moment of inertia about the z axis, then it will be also called polar moment of inertia. So it is already explained what is the polar moment of inertia, and then it is not now again required. Okay. Now, what is this formula you have now? This formula validation you need to write. Okay, it is important. So it is nothing but tau by r is equal to t by j is equal to g theta by l. So remember, this formula is what valid only for valid valid only for valid only for circular shaft. If I say circular shaft means both solid and hollow. Okay. One more thing you need to remember. It is not valid. No, not valid. Not valid for, remember, composite shaft. Composite shaft means with the two different material or more than two different material. If it is made, then it will be called as a composite shaft. Okay. So for composite shaft, it is not valid. This one you need to remember. Fine. All right. Up to here it is done. Now we'll go for the assumption for this. Assumptions. So just like for bending of beam, you had seen Euler's a beam and there was assumption. So here also we have assumption. So in assumption, first point, pure bending. Okay. So means we do not have any, it is valid for our assumption here you have taken for the pure torsion. I said I think bending. No. For the pure torsion means there is no bending. So if there is no bending, only pure torsion or pure torque is what available, then it will be the valid condition formulation is valid for the continuous, I mean, calculation and all. So this is the first assumption. Okay. Should be pure torque. That's the mean of it. Should be pure torque. And what is the pure torque? So let me write first pure torque or pure torsion, and which is obviously impossible thing. But anyway, we should be aware with the pure torsion. So first first assumption is the bar is acted upon by a pure torsion or pure torque. What is the pure torsion? So pure torsion means pure torsion means torque may be does not equal to 0. It may be maximum or minimum, both condition. It may be maximum or it may be minimum, doesn't matter, but torque will be there. But what about shear force? SF, shear force will be 0. Next, bending moment will be 0. And last is axial force, which means AF will be 0. So that's the mean of pure torsion. Okay. What is the Euler-Bernoulli assumption for this? So first you have written it is for the pure torsion. Second, no distortion. No distortion in the shape of cross section after the torsion. Okay, no distortion after the torsion. This is the assumption, very important assumption. Okay. What is the next assumption here? The material obeys Hooke's law, just like for the bending moment I had given assumption. So here also the material, so if I say it obeys Hooke's law, that means the material which is used for the shaft should be elastic. No? Material obeys Hooke's law. Okay. Cross section rotate as if rigid, and that is every diameter rotates through the same angle. It doesn't mean that's the called no distortion. It doesn't mean at one end it is deformation is more or it is rotated more, and at another point it is rotated with some different angle. So it should not be there. I mean, throughout the diameter it should be a same angle. That's the mean of it. So I must write for cross section rotate as if rigid, that is every diameter rotate through the same angle. Through the same angle. Through the same angle. Okay. Next, fifth, torsion is constant. Torsion is constant along length of shaft. Along the length of the shaft. Okay. Last, whatever the material you are using, material is isotropic and homogeneous. Okay, these are the points you need to remember. Isotropic and homogeneous, already I had explained what is the isotropic. In all direction, if properties what showing same, it is isotropic. And homogeneous means throughout the section of the bar, if the composition is what same, the same kind of material is what used everywhere for the designing of the shaft or any member, then it will be called as a homogeneous. Otherwise, other name is what? Heterogeneous. That means different materials used for the uh, making that bar and all. Okay, so that's the reason here it is clearly mentioned it is not valid for the uh, composite shaft, because in composite shaft means different material will come. Composite means what? Different material. So different material means it will be different material. That means it will not be a homogeneous anymore. If it is not homogeneous, then this will not be valid actually. Okay, so I think it is clear now. So this is what assumption. Torsion equation now you know. Now moving ahead, we have a polar section, then solid shaft and hollow shaft. How to calculate that polar moment of inertia, that already I have discussed. Then we'll go for the arrangement of shaft, that is series and parallel. So before that we have this analysis which is called polar moment of inertia. In fact already I have given, but in short here also I will write for the solid shaft and hollow shaft. So J, polar moment of inertia. In first lecture, in basic lecture, I had given for the solid and hollow, both I had given. So for solid shaft, suppose this is the shaft here. And the diameter for the shaft is D. And we have a hollow. So for the hollow, okay. So small diameter is nothing but a small d. It is capital D. Okay. This is the axis. Fine. So if you write the both cases, polar moment of inertia. So here you have that derivation of this I already had discussed in my first lecture. So you go and watch that. Pi d to power 4 divided by 32. And here it is pi by 32 d to power 4 minus d to power 4. Okay. All right. D is the external diameter. And small d is internal diameter. All right. So already I have discussed this, but here again I have mentioned, so remember it. This will be very helpful for you. One more term is very important I need to mention here, called torsional stiffness. What is the torsional stiffness? That also need to remember. Sometimes this value will be given to you. Torsional stiffness. So if you remember, suppose this is what a spring. This is the force applied. Once force is what applied, you just say the in this beam after the force application F. So you may get the deformation X. So its stiffness of a spring is nothing but K. So F is equal to Kx. So what is K? K is nothing but F by X. What is the F? F is the force. What is X? It is deformation in spring, it is in along x-axis, so sometimes it is called displacement or deformation even also you can say. And what is K? K is the stiffness. Okay, so similarly for the shaft we have a torsional stiffness. So torsional stiffness is basically denoted by KT. This K is simply stiffness of the spring. If I say KT, like in toys and all, you had seen the circular plate spring like this in toys, no? That spring will be like this. If you toys and all, if you open, then you may get this type of spring called strip spring, circular spring. Okay, so for this, what is the stiffness? KT, called torsional stiffness, because in toys you will rotate, there will be key, and if you rotate and then leave the toys, then toys will move, right? You had seen many times. So it is why, because of the torque you are providing, and torque, that torsional energy will be saved in spring, and once you leave it, then it will be released, that energy, so it will move in forward direction. It will, that energy will be converted into rotational energy, and it will rotate, it will move in forward direction. What is KT? KT will be T divided by theta. From the formula, if you check here, the standard formula, what is the standard formula? You have here tau by R is equal to T by J is equal to G theta by L. From these two formula, if you check what is this, T by J is equal to G theta by L. So what will be T by theta? It will be Gj by L. Remember this formula, it's very important. In exam they are asking this. Okay, Gj by L. This is called torsional stiffness. So and also it is defined, what is the mean of it? So it is defined as torque per radius twist. Torque per radius twist, called as torsional stiffness. So that you need to remember. Okay. Now, so moving ahead, now because we are talking shaft here, so if this is the shaft, and purpose of shaft I have discussed already, it is basically used to transmit power from one system to another system. For example, I had said, suppose we have a one end we have a turbine, another end we have a compressor. So power from the turbine will be transferred to the compressor, that already we have discussed like this. This is what diameter. Okay, so what is the power transmission here for this shaft? What is the power transmission? So power transmission, because it is rotating, because of the torque it is rotating, so obviously you will have angular velocity. Angular velocity means the velocity around the axis, called angular velocity. So because of twisting moment, definitely it will rotate about the axis, so angular velocity will come into picture. So what will be the power? So power is nothing but whatever the torque you have applied to the shaft into angular velocity. Okay, torque into angular velocity. Now you know very well that T, and what is the angular velocity? It is 2 pi n. So P is equal to 2 pi nt. This formula many times you have seen. Okay. Now, if this is the formula, then here this n will be in revolution per second RPS. But if you divide it by 60, then this n will be RPM. You know that, okay? You know that. So this formula is important. P is equal to 2 pi nt divided by 60. You need to remember, sometimes it will be useful for the numerical. It is very basic, you know very well, but need to write here because we are talking about the torsion, shaft and all, so it is necessary. Hope this one is clear. Now, obviously that HP conversion and all you know, so no need to write. So two things based on the stiffness consideration, based on the shear stress consideration. By two way we have to calculate the safe diameter. Okay, so if you want to discuss the safe diameter of the shaft, okay, like whatever the diameter of the shaft you have taken, it is safe or not, how you would know? Okay, how you would know? So we have a safety purpose. For based on that we have analysis of the it's a very simple safe diameter. How you would know this? We have a two method to know the safe diameter. Which one is safe? Okay, so first one is called shear stress consideration. Shear stress consideration. Second one is stiffness consideration. Stiffness consideration. What is the formula of the, you know the standard formula, tau by r is equal to T by J is equal to G theta by L. So this value tau by R, shear stress tau by R is equal to T by J. This here we have a shear stress, hence it is called shear stress considerations. If you use this formula, then R, that means diameter, you will get here in R, and J is the polar moment of inertia. So J is also in form of in terms of diameter, and R obviously it is a radius, so it will be diameter by 2. So one diameter you will get by this formula. Another, I mean you have used this first one. See, if you check, one is first this formula, so here you will get diameter. Similarly, if you use the another formula, so in this case also you will get diameter because you have a polar moment of inertia. So this T by J is equal to G theta by L. So check stiffness I have given to you. Stiffness means T by theta. Just now you had seen stiffness, no? So second formula is what is stiffness consideration. So here also you will get diameter. In both cases you will get diameter. Here you will get diameter, and here also you will get diameter. So what is the safety condition? Okay, safety condition, because diameter will get in both cases. Safety criteria. What is the safety criteria? So remember, if question will be asked, suppose anywhere based on this, so what is the safe diameter or what is the safety criteria for the shaft in terms of diameters? Immediately use both formula, you get the diameter, and in both cases you will get diameter, but higher value of diameter I will write, take higher value of diameter, okay, of both cases, of both cases above for overall safety. This is the safety criteria. Okay, this is the safety criteria. If question will be asked, sometimes question will be asked to you, okay, what is the safe diameter for the shaft? They will give all the value. You need to calculate diameter with the help of both coupled formula and get higher diameter, and that diameter will be the safe diameter. Below, suppose one diameter you got 20 mm, another it is 15 mm, so safe diameter you need to take 20, because if you take 15, so chances of failure is there. That's the mean of it. All right, fine. Now if I say go for the calculation of the maximum shear stress, so how to get that? So if I say maximum shear stress for the shaft, so for both cases, so maximum shear stress you are going to calculate, okay, for both. It is the solid shaft, and this is very frequent, they are asking in exam, okay, hollow shaft. So this is very frequent, they are asking in exam. All right, so you are talking about the solid shaft, so this is what solid shaft here. Diameter for this is what, D, okay, and you just say torque is applied here, T. Similarly we have a hollow shaft here, okay, so this is small d, this is the capital D, and obviously here torque is what, applied, same amount. Then what is the formula? Check. Tau by R is equal to T by J. So if I say tau max, listen carefully, tau max, so that means T by J into R max. What is the mean? T by J. What is the R max? Means capital R. R, small r is the radial distance. I told you many times, from the center, suppose this is the center, so from the center small r is the distance, and if it reach over the surface of the shaft, then it will be the, here it will be the radius, yes or no? So small r max means it will be capital R, that is the radius. So, and similarly for this also, so for solid and hollow shaft, if you write what is the J, I had given the formula pi by 32 d to power 4. So what is tau max? So it is T by J into R. Now you need to keep this value J and R. So keep that value. So you will get T divided by J is nothing but pi by 32 d to power 4 into R is nothing but d by 2. So if you solve this, then tau max you may get. What is the value? It will be, take 32 upside, so it will be 32 by 2, it is 16. Torque divided by diameter 1 1 diameter cancel, so pi d power 3. So this is for solid. Similarly, you have to do for the hollow shaft. So you know that tau max formula is what? If you are writing max, so it is T by J into small r will be capital R. So capital R means this value. You can write the value of T divided by J. What is the J for hollow shaft? You know, it is pi by 32 d to power 4 minus small d to power 4. Okay, into R will be capital D by 2, because you are writing tau max, so this small will be capital R. I mean maximum value of the small r will be radius only, radius of the, you know, the whole section. If it is hollow also, for what is the maximum radius here, you can check what is the maximum radius. It will be D by 2. If I say maximum R max, maximum radius, it will be D by 2, simple. So bigger diameter divided by half will be the maximum radius. Okay, so you just do it. So what will be the tau max for the hollow? You check this diameter you have here, so it will better you don't cancel, only 32 and 2 will be 16, so I must write T divided by 16. I think it will come, because 32 divided by 2 it will be 16 T, and diameter will come here, so better you write diameter also 16 TD divided by pi d to power 4 minus d to power 4. This is what tau max. For both cases it is very important. Okay, sometimes directly they will hit questions, so that time better you remember the formula. Derivation only 2 to 3 lines, so that's the reason I'm deriving, otherwise derivation not required. But just for your understanding, because here I'm deriving, so numerical part is what now will be cleared in this way. Okay, so this is the solid shaft and hollow shaft here. Solid shaft and hollow shaft. And hollow shaft. So one kind of question they are asking, the comparison. That comparison for what? Comparison for the strength they are asking, which one is more stronger. Okay, so sometimes they will ask strength, sometimes they will ask that comparison of the weight. Okay, so sometimes they will ask the comparison between both in terms of strain energy. So this type of question for one day exam they are asking. Okay, which one having more shear stress, I mean can sustain more shear stress, which one, solid or this hollow, for the same amount of torque and all, they will give the criteria. So we have to compare this. Okay, so for the, I will write for the same weight and same material. Okay, so criteria will be for all different cases, criteria will be changed. Like if you are talking about the strength comparison, so you talk about same weight, same material, same length, and same shear, maximum shear stress. If you are talking about the weight comparison, so what will be the constant thing, same torque, same material, same length, same maximum shear stress, like that. Okay, so I will write both cases. So we have derivation, but derivation I say are not required. So now we have solid shaft here, so this is what solid shaft here, length L, same diameter, and this is what okay. So we have this small d, and this is capital D, small d and capital D. So first we'll take example. What we are going to compare? We are going to compare the compare the strength. Okay, so now you need to mention we are having the same weight, same material, same length, and tau max. Okay, for first you are going to talk the strength comparison. Strength comparison. So this will be for same weight, means both solid and hollow both are having same weight, same material, same length, and for both tau max is what? Same. For this condition we are going to compare the strength of solid shaft and hollow shaft. So what is the strength? So if you talk about the strength, so that strength is what related to the torque. Strength comparison, if you are going, then it means you are talking about the torque. Okay, I mean up to what maximum torque that shaft can sustain that twisting moment. That's the mean of it. Strength of torque, strength comparison means you are going to check the twisting moment for the both shaft, I mean both shaft, for solid and hollow, which one is what can sustain more twisting moment, can resist more twisting moment. That's the mean of it. Okay, so the formula, as I told you, we have derivation not required here. You remember the formula only, that's all. So the formula is what? T hollow divided by T solid. And here the formula is n square plus 1 divided by n square minus 1, where n is capital D by small d, where n is capital D by small d. You can say external diameter of hollow shaft, which is nothing but capital D. Okay, and internal diameter is nothing but small d. So if you compare this, then this result you will get, number 1. Okay, what is the mean of it? If you check D, capital D by small d, that means it is greater than 1 always. There is no doubt about it. It is greater than 1. So if you check this result, n square plus 1 divided by n root of n square minus 1. If you calculate this value, any result, if you get, and it is root also here, n square minus 1, it is root also, you just take suppose 2, just for example. So 2 square, that means 4 plus 1, 5. In bracket, or better you take 4, better, in that way root will be easy to calculate. Okay, or you take 2 only, no problem. So this is 5 divided by 2, it will be 2.5, again root of 2 square minus 1. So 2 square will be what? 4 minus 1, it is 3. So root 3 you have to take, 1.73. So 2.5 divided by 1.7. So that means if you check the strength wise, so this hollow is greater than solid. Remember, not always. It is not always. we have condition. For this condition only, for this condition, same weight, same material, length same, tau max same for both, then this hollow can resist more twisting moment compared to solid. I mean, solid shaft will easily break down. I mean, it will easily fail compared to hollow when you are going to check the strength. And for the both shaft, same weight, same material, same length, and for the same maximum shear stress. I think this one is clear. Now if you go for the in fact this value, this is number one. Number two will go for the two. You just talk about maximum shear stress. So just now only you had calculated the value. It was tau max for the solid. You had calculated something 16t divided by pi d cube. 16t divided by pi d cube, and tau max for hollow. It was, check, 16 TD divided by pi d to power 4 minus power 4. Okay. Now here, if just make a point here, if small d is capital D by 2, small d is capital D by 2, then check what will be the tau max hollow. If small d is means internal diameter is what, exactly half of the external diameter of the hollow shaft. So you just keep this value. So what you will get? We'll find this. It is nothing but 16 TD divided by, if you solve this, you may have a pi. This value will be 15, I think. 15 pi due to power 4 by 16. This value you may get. Okay, so check this. Now this is the value. If you compare this value, tau max divided by hollow and tau max divided by solid, check what result you will get. So it will be 16 TD. DD cancel out. Better I will cancel this D. 16 T, 16 into 16. Wait. So 16 into 16, it will be those 256 torque divided by 15 pi due to power 3 divided by solid 16 t divided by pi due to power 3. If you check, if you solve, so again this 16 we have, so it will be in cancel out, so you may have 16 divided by 15, rest this value pi d cube divided by pi d cube by pi d cube cancel out, t by t cancel out, so 16 by 15 you may have. So check, this is what, greater than 1. So again, if you compare the maximum shear stress, so tau max, that's the reason hopefully now you are getting why we are talking about the solid hollow shaft in many cases. Hope you are getting now. So this is the comparison, is maximum shear stress wise. So maximum shear stress that a hollow shaft can resist, compared to solid one. Hollow shaft can resist more shear stress or maximum shear stress, you can say. So when it is possible, when it is the same material, okay, you are talking about the same weight, same material, then this result you may get. Okay, fine. Chances like, okay, this type of question, theoretical question nowadays they can ask easily. Okay, so you have to be prepared for such type of analysis, and it's very simple, it's not difficult. You take your time, write formulas, compare by your own, check the formula, remember the formula. Even if you want to derive any, take any textbook, in all textbook it is available, which go and derive also. So that's all right.